Okay, now we're going to change gears a little bit and talk about interference and diffraction. And I have some good news about interference. We've talked about it with mechanical waves, and everything is going to transfer directly to electromagnetic waves, to light waves. So what is interference? Well, any two waves can live at the same place at the same time. They can superimpose, and they can reinforce each other, and we call this thing constructive interference. Or they can cancel each other out, and we actually call this thing destructive interference. True for light waves, true for sound waves. What we're seeing is we're seeing the sum of the amplitudes of the combining waves. This guy looks pretty familiar. I think I've showed it to you once before when we talked about mechanical waves. Here we have two waves. They could be light waves, could be mechanical waves. These guys are going to add together. They're going to reinforce. And again, we would call this constructive interference. And in the language of light waves, what we're going to have is we're going to have something that is relatively bright. The amplitudes are adding together. Here we have two waves that are out of phase, so wherever this one is up, this one is down, and vice versa. These guys are going to cancel each other out. Fancy word for that is we call it destructive interference. In the language of light waves, this is going to essentially be dark. So bright and dark. Kind of the fuzzy area in between, we don't really have a fancy name for that. They're just going to partially cancel each other out, so it's neither going to be bright nor dark. Now, before I talk about it in the language of light waves, I do want to come back just to mechanical waves because they're conceptually easier to understand. Suppose I had a source right over there and a source right here, and these guys are dipping into the water at some frequency. Then, of course, they're going to send out spherical waves, and we would be talking about wave crests and wave troughs and so on and so forth. And what you could kind of see is you could kind of see these guys are going to live at the same place at the same time, and we're going to regions of constructive interference and regions of destructive interference. So along this path right over here, you can kind of see destructive interference in these regions right over there. They're canceling each other out. There's going to be regions where it looks a little bit stronger, and they're going to be adding together. Now, in the language of light waves, the same exact thing can happen. Suppose I had a light source and it was shining some light waves, and I had two waves kind of like this. Here, that's a crest and that's a crest, and here's a trough and here's a trough, and here's a crest and here's a crest. These guys are going to add together. What we're going to do is the amplitude is going to add, and we're going to get a bright spot. Consider for a second, though, a pair of waves that were completely out of phase, where when this one is up, this one is down, and vice versa. When these two guys arrive on some screen, then they're going to cancel each other out. We're going to get destructive interference, and we're going to get a dark area. Now, this slide just kind of says everything that I already said, but it's worth reiterating because it's kind of important. When light arrives in phase, we're going to get constructive interference. We're going to get a bright spot. And when the light is out of phase, and technically it's been shifted by half of a wavelength, I'll let you convince yourself of that, we're going to have destructive interference. They're going to cancel each other out, and we're going to get a dark spot. Now, how can we get light to arrive in phase and out of phase? Well, we can actually put it through some slits, and we have a special name for this. We're going to call this a double slit pattern, and technically we're going to say that it's Young's double slit experiment. Consider I had some light arriving on two slits like this and like this. Then Huygens' principle would say that these guys are going to act like point sources, and they're going to start sending out waves, kind of like what we saw right here. This would be like one slit right here, and then the other slit right next to it. Well, what's going to kind of happen is it's going to send out light waves, and these guys, when they reach the middle, directly in between them, then they're actually going to be in phase because they travel the same distance. So let's go ahead and count them. 1, 2, 3, 4, 5, 6. Let's count this guy. 1, 2, 3, 4, 5, 6. And when this one is up, and we're going to, lo and behold, get a bright spot. So they're in phase. However, consider a spot a little bit lower, or it could be a little bit higher. I know right here I'm going to have the light arriving in phase. I'm going to see a bright spot, but there's going to be somewhere down here where they add together again. 1, 2, 3, 4, 5, 6, 7, and this one's going to have 1, 2, 3, 4, 5, 6. So the top one has gone a little bit further, but they're still arriving in phase. Now, here's something kind of interesting to think about is we know that we're going to have a bright spot right here in the center, and we know down here we're going to have a bright spot. The top one's going to go one full wavelength longer than the other one, but they're going to line up and get constructive interference. Now, if we were to look somewhere in between those two bright spots, what we would see is the top one's going to travel just 1/2 of a wavelength further than the lower wave, and they're going to line up such that they get destructive interference. So you can kind of see that this one right here is going up while this one right here is going down, and they're going to cancel each other out, destructive interference, and we're going to get a dark area right there. You could also argue that right up here we would get a dark area and a bright area and a dark and bright and so on and so forth, and then down here you could say dark, bright, and so on and so forth. And it does turn out that's exactly what we see. If we were to have some light, and it does have to be a single wavelength of light, it can't just be white light, 2 slits, and you go ahead and you take a look at the interference pattern, we're going to see a bright spot, and then a dark spot, and a bright, and a dark, and bright, and dark, and keep on going. This right here is kind of complicated, but it pretty much shows everything that we're talking about. Bright, dark, dark, bright. So this is kind of what the interference pattern from 2 slits is going to look like. And again, what we're seeing is we're seeing the superposition of waves, and we're seeing constructive and destructive interference when they're in phase and out of phase. Now, what are some implications of this double slit experiment? Well, it actually gives us a way to measure the wavelength of the light that we're illuminating it by, and what you're going to do is actually you're going to see this in the lab, and we'll go ahead and talk about that when we get to the lab. But this experiment also proves that light must be a wave. Sometimes light is going to exhibit wave-like behavior, other times maybe it's going to exhibit particle-like behavior. But back when Young was doing this experiment, they were trying to prove, is it a wave, is it a particle? And waves can cancel each other out. We can have constructive and destructive interference. Particles can't cancel each other out, so it's kind of inconceivable that that could happen. So what this experiment proves is light is definitely a wave, at least for right now. Now, there are other ways where we could have light cancel each other out by shifting it a little bit. And I showed you the double slit, but let's talk about another way, and this would actually just be thin film interference, and this is kind of why oil on the parking lot looks kind of shimmery-like. Suppose we had a light source, we had some light coming in kind of like this, and here I'm showing 2 waves of a similar color, and we have some glass, then we have some air, and we have some glass. Then what's going to happen is every time light hits a surface, it has a choice. Does it go through it, or does it reflect, or is it absorbed? But let's talk about just the reflection and the refraction bit of it. So at this surface right here, light has a choice. It could reflect or it could go through it. Let's just for right now say, okay, this one could exist, but we're going to not deal with that one because it's kind of confusing for right now. Let's take a look at this blue one. The blue one's going to go through the glass. It's going to hit this surface right here. And because it's on a glass air, it's more likely to reflect. So here we have this wave kind of coming like this. The black wave, let's just say for a second that it makes it through it. And so it's going to come down here. It's going to bounce off of another glass surface. It's going to come back. And you can kind of see that these guys are out of phase. So our eyeball is going to see destructive interference. It's going to see something that is relatively dark. Other wavelengths, maybe the spacing is such that it's going to shift them just right so we get a bright fringe. So what we're looking at is the reflection from the upper and lower surfaces of the 2 glass plates. Now, some applications of this is something called Newton's rings, and if we were to have some glass and then put it on top of another piece of glass and allow air to be right here, what we're going to see as this thickness is going to increase, we're going to see constructive and destructive interference as the one wavelength, the one that goes through right down here, is going to travel roughly half a wavelength or a full wavelength longer than the other one. So we're going to see this pattern where it's going to be dark, bright, dark, bright, dark, bright. And these are actually called Newton's rings. You may be saying to yourself, well, who cares? Well, actually, lens makers use this very phenomenon. What they do is they create, let's just call it a template out of some glass, and what they do is this is the exact shape of the lens that they want to measure. Let's just say that it's a pair of glasses or something like that. you go ahead and you put the lens in there, and if the lens that you created is perfectly matches up with the master, you're not going to see anything because these two surfaces are going to line up, and far better than what I drew it. If these surfaces do not line up, suppose there was a defect in the lens where it I don't know, did something kind of like that, then you're going to see Newton's rings, and you know that you didn't machine your lens properly. Other applications of this is why oil is going to look like that. Essentially, we have a layer of oil on top of water, and it's going to act pretty much like glass on top of air on top of glass. One thing to bear in mind is that different wavelengths have different colors have different wavelengths, and the spacing is going to cancel some out and not cancel other ones out. So we can see patterns on oil that look like this. One thing to note is the colors that we see are actually all the subtractive colors. We're not going to see any primary colors, essentially because we're taking colors away. Now, keep in mind that the thickness has to be just right in order for this cancellation to occur, and different wavelengths are going to have different frequencies. So this kind of shows exactly what I was talking about with the gas or the oil on top of water. We have light coming in. We're going to have one wavelength bounce off. That's the blue one. This black one is just going to go half of a wavelength longer. It has the same frequency. And we're going to come up here. This one's coming up. This one's coming down. And we're going to cancel these things out. And we're not going to see that particular color of light. This thickness may allow destructive interference for this particular wavelength, but other wavelengths it's going to allow constructive interference, and we would be able to see those. This one right here, we're saying that it's blue light, and so it would cancel it out. And the thickness has to be just right in order for this to happen. If this thickness was a little bit larger, then the path length of the black one might not be enough to cancel out the original wave. And just kind of a real-life application of this, back in 2010, we were flying out of New Orleans, actually, and we flew over the Gulf of Mexico over that Deepwater Horizon spill, the one that put all that oil into the Gulf of Mexico. And you can actually see all the ships right here trying to contain it. And you can definitely see, here's the water, and you can see the shimmery oil just right here. So, real-life application, this stuff really does actually work. You can also see this with bubbles. It's pretty much the same thing as air glass and then glass, or air glass, air glass. Same thing, we're going to see interference. The thickness has to be just right, and we're going to cancel some, but not all the colors out. Again, do note that these are the subtractive colors. We're going to see magentas, yellows, and cyans. We're not going to see the primary colors. Just a quick little check your neighbor type of question. Suppose we had violet light that was canceled out by some type of thin film. Then what color are we going to see? And our choices are red, orange, green, and violet. Well, violet light is canceled out, so it's definitely not that one. And then I'll redirect you to this from chapter 17. The closest one that we have right here is going to be where we don't have any violet light. This one kind of takes out the blue. And this one would be yellow. But kind of in our mind's eye, we don't see yellow on here. The closest one to this guy is probably going to be orange. So we're going to go with B here. Now, when do we see interference? We're actually going to see interference with all mechanical waves, so sound waves, with light waves. So this one is going to be C. Now, the last thing I want to kind of talk about is what happens if we have more than one slit. I've kind of talked about the case where if we had some card and it had two slits on there, that we're going to see bright, dark, bright, dark, bright, dark. But I've actually kind of talked about just a single wavelength. I said that we're going to shine monochromatic light on there, which is a fancy word for saying just one color, just one wavelength. If, however, we were to get a bunch of slits together, kind of like this, and we were to shine not just one wavelength on there, but a bunch of wavelengths, maybe even something like white light, then what we actually have is something called a diffraction grating. And all this really is, it's going to be a bunch of close slits, and this is going to let us take a look at the light. What it's going to do is it's going to disperse the white light, just like the prism did. And we're going to separate the light out into a bunch of colors, and that's kind of useful if we want to analyze what frequencies are in a particular light.